Hi, folks. Today we reach peak quantum weirdness. I've been putting it that way, and I think it's true, but that maybe doesn't accentuate the positive as much as we should. Calling this stuff weird is to say that it's extremely surprising, that it teaches us new, deep, exciting things about the kind of universe we live in. So, I want to have some sympathy with how hard it is to get one's head around some of this material. But it's really important to do so. It's important to understand the basic nature of the universe we live in. And so I think this is an appropriate subject with which to cap the main story. Remember, we had kind of a prequel, what science might believably be, Popper versus Kuhn, etc. Then we started telling a story about physics and astronomy and ways in which what we have come to recognize as science has grown and changed, and one step forward, one step back, etc. We're going to end with stuff that's genuinely less than completely understood. And at this point, you're going to have a pretty up-to-date sense of what's going on in one cutting-edge aspect of physics. And hopefully the connections to philosophy will emerge pretty clearly as well. This raises deep questions about what space is, what it is to be one thing rather than two things. The philosophical issues are very much enmeshed in the physics. So let's jump in and try to keep morale up. We're almost done with physics, but I do think this very much merits your time and attention. So, as we've seen all along, and this is a bit of an oversimplification about Einstein, but this is the usual story, and it's not wrong, even if it's not completely accurate at the level of detail. Einstein defended philosophical common sense in the face of standard or Copenhagen interpretations of quantum theory. That is to say, quantum system, particle, wavicle, whatever you want to call it, has classical features, even if we are never able to simultaneously get values for all of these features. And Niels Bohr, the main proponent of Copenhagen views, resisted that, saying physics is about what we can measure, and so it's meaningless to make claims about what's going on behind the measurement. Physics is about experimental setups and making testable predictions. We'll talk about the ways in which quantum mechanics is and isn't testable in a little bit. And so Einstein really struggled to try to find a way to show what he firmly believed, at least for much of his career, namely the incompleteness of quantum mechanics. That's why Einstein is known as defending a hidden variables view. There are real features of reality, Einstein thought, that are not captured by the the standard interpretation of quantum mechanics, according to which the math does not present the particle as having a particular spin or position and velocity at the same time, a spin on more than one axis, I should say. Those physics details are not your problem. So Einstein kept coming back at Bohr, and he helped Bohr refine and develop his views. In maybe the most entertaining exchange, Bohr was really stumped by an objection Einstein had involving clocks and quantum setups, until Bohr realized that Einstein had failed to fully take general relativistic effects into account, and once Einstein did, he didn't have an objection to quantum mechanics. Later, Einstein, along with Podolsky and Rosen, you don't need to know those names, just call it the EPR experiment. This is the culmination of Einstein's attempts to bring out the alleged incompleteness of quantum theory. So you need to understand just the basics of it. I am not holding you responsible for a lot of nitpicky details, but you do need to have a clear understanding of the basics so that you can see how this stuff works. DeWitt talks about it in terms of polarization. This is what goes on in your sunglasses, about how some photons go through and some don't. According to quantum theory, as classically interpreted, there's just a random root probability that a given photon will go through your polarized sunglasses. The details of polarization don't really matter. It is one of a family of twinned properties. Twinned properties are such that Maybe the easiest example to understand, if we decompose a particle into two smaller particles that shoot out at opposite directions, we know they'll shoot out with the same velocity, for instance. So by learning something about one of the twinned particles, we can learn something about the other twinned particle. Polarization is among the twinned properties, but there's no deep mystery about why the photons are twin, why they have the same property. So if your polarization detectors are set up identically, and you know you're dealing with twinned particles, and those are pretty easy to generate, you know that if one is detected as having up polarization, the other one will be detected as having up polarization. So Einstein, Podolsky, and Rosen try to show, based on that, based on the phenomenon of twinning, that the best explanation for the twinned properties is that each particle has a given polarization all along, even when it's not being measured. Bohr and other proponents of Copenhagen interpretations are committed to denying that. And you should remind yourself, based on our two previous chapters in DeWitt on quantum theory, why the standard interpretation denies this, right? The standard interpretation says it's meaningless to talk about what's really going on when the system isn't undergoing measurement. We can give the math a very thin physical interpretation, but that's the most we should do, and the math does not give the photon a polarization prior to a detection being undertaken. So the idea on the standard interpretation is whether you're going to get an up or a down polarization is random. But the twinned photons are both going to give you the same polarization result in identically configured detectors, right? And so Einstein, Podolsky, and Rosen try to convince you via a thought experiment, we'll work through that argument in a second, that this is best understood as showing that quantum theory is incomplete. So the thought experiment says, send twinned photons off in opposite directions. Set up polarization detectors such that one is just a tiny bit farther away from the emitting source than the other. Since we know that they're twinned, if you measure the first photon as up, you know that the second will be measured in a microsecond later as also having up detection, right? So whether it's up or down, polarization is random, but it's highly non-random whether the two of them will agree. It doesn't follow yet that the photons had the properties all along. What do you need in order to establish that and show the incompleteness of the standard interpretation? You need the locality assumption. The idea is nothing over here can possibly be informing or influencing what's going on over there if there's no time for even light to get from here to there. So this was why Newtonian gravity was thought to conflict with special relativity, right? You can't have instantaneous action at a distance. So we'll pretend here for a second, physicists do talk this way, that photons are conscious and capable of understanding things. There's no way for the photon all the way over there to know what's going on at the polarization detector here. So this perfect correlation among the twin properties has got to be explained somehow, right? We don't think it's just a random fact that all dimes look alike. We need some explanation of why there's this perfect correlation between what goes on at the two detectors. So since the detectors are far enough apart and the time difference between them is small enough, given locality, right, there's no way for any influence or signal to go from the first polarization detector to the second. And so if it's not some cause, some signal, some message, something being sent from here all the way over there, right, and it would have to go faster than light, it must be that the photons had their polarization all along. So given locality, the standard interpretation is wrong. The standard interpretation denies that the particles had their polarization all along. The math does not present a given polarization as existing prior to measurement. If that's seeming foreign to you, maybe review the stuff about interpretations of quantum theory. All right, I'll give you a break to cool off your brain in a second. The last thing I want to note before breaking this lecture up into some smaller parts is this is another thought experiment. Like Galileo's thought experiment, Einstein has given us some influential thought experiments. This involves an explanation of what you would detect. You can't do a detection saying a direct detection saying there was a polarization all along. You can't measure what would be happening if you weren't measuring. Okay, we are going to keep exploring quantum theory and non-locality. So this is just part one of our lecture on DeWitt's chapter 28. Hang in there, folks. Pretty cool stuff.